welcome to 7 volts. I am Hemant. In this video, I'll be showing my new project where I'll be testing my Master Transmit API of I2C communication protocol. I have configured this as master and this as slave. Whenever I press this user button on the STM32 board, I'll be sending welcome to 7 volts to this board through I2C communication protocol. Whenever I press this button, I should get welcome to 7 volts in my serial monitor of Arduino IDE. So let's see that. There we go. So let's get started. So in this video, let's learn the basics first. Let's know why we needed I2C communication protocol when SPI was already there. In SPI there are many drawbacks. So in SPI it always works in full duplex mode, and there are no acknowledgement or checking whether both sides there are hand checking, or there is no arbitration. So you can also not connect many number of peripherals. You need dedicated slave select pins. So Philips Semiconductor developed a new communication protocol named I2C. It stands for Inter-Integrated Circuits. The name suggests that we can connect n number of PCBs to this using only two pins, that is SDA and SCL. And we also need to calculate the pull-up resistor, which is here, and there is a dedicated formula for that. By using that formula, we can calculate the pull-up resistor values, and there is a limitation the number of peripherals you can connect. There is a maximum limit to the bus capacitance. So until we reach the maximum bus capacitance, we can connect the peripherals. It uses only two pins, that is SDA and SCL. In this project, I have connected my PB9 to that A4, that is SDA, and this is PB6 to A5, and this is serial clock. I can also show you my waveform which I generated using a logic analyzer. So you can also notice two things here, that is start bit and a stop bit. In this, start bit is done when the serial clock is high. The SDA line is pulled down. You can see here. As you can see here, the serial clock is high and SDA line is pulled down. When the state is high, you need to pull down the SDA line. Then only it considers it as a start bit. And the data is being sampled when the serial clock state is high. The data gets sampled. The first 7 bits will be the address, and the last bit will be the mode, whether to write or read. And here it's write. And from now, we'll be just sending the data, 8 bits of data. And you can verify the values. It decodes to welcome to 7 volts. This is W, E, L, C, O, M, E, and this is space. Similarly, we can decode all the bits. Now let's look at the last stop bit. It's very important to understand the stop bit. When the serial clock is high, the SDA line is pulled from low to high. This is the stop bit. And after each bit, there is an acknowledgement bit sent. The slave doesn't pull the SDA line high. This suggests that the bit was acknowledged by slave. As you can see, SDA is low, and when SCL is high, this is the acknowledgement bit. Now let's look into the code. Here I have declared the address of my master as 61 and the slave as 68. You should get this by looking into your Arduino sketch. Here I have declared my slave address as 68, and I'll be calling this here when I start the I2C bus as slave. So you need to note that. And I have my data buffer here, and these are two global declarations of my handle structures. Let's get into the main. First, I will be initializing my GPIO button. Then I will be initializing the I2C GPIO pins. Next, I will be initializing I2C. Then I will be enabling the I2C. Then I will be waiting for the button to go low. When the button goes low, I will just send the data from the buffer. And in I2C init, I'll be just doing some handling configurations here, where I'll be enabling the acknowledgement bit, and I'll be giving my address, and this should be my master address, and this is not needed exactly. Why? Because in standard mode we have the duty cycle to be 50-50%. So this thing is not needed. It's only needed where we'll be going into the fast mode. I2C supports different modes. This is my source code of I2C driver. If you want a detailed video of this, do comment it down. I will explain this. This thing takes a hell lot of time to explain. So do comment if you really need it. I'll be dropping my GitHub repository link in the comment section. Do refer it and execute this in your bench. The major things to note here is, make sure that none of the boards backfeed the power to the other boards. There should be a complete isolations of the boards. Use this logic level converter to isolate these two boards, and make sure the pin connections are made properly, because if there is any loose connection, I2C communication protocol really won't work, and this can be very frustrating. So make sure that you have connected to exactly the pins which you have configured, and all pins are intact, and there is no loose connections. This was the video, and thank you for watching. Bye.